Excuse me. This is Kurt Munson from HPM nCode. Good morning, good afternoon, good evening to all of you. Welcome to today's webinar entitled, Why Does Your Product Break? This is part of nCode's continuing webinar series on things related to durability and vibration analysis. Now the question, why does your product break, may seem a little bit daunting. This is a challenge. It's a negative, you could say. It's a negative lead-in. We obviously don't want things to break. So you could look at this as a scary scenario, things breaking. But you can look at this as an upside too. We're all engineers, and part of our mission is to engineer our way out of challenges. So if the challenge is why does your part break, we need to think today about how is it that we as engineers can work to ensure that they don't. And the good thing is, in doing so, number one, we'll have a product that's more durable, and number two, we'll be more valuable as engineers ourselves. So that's me. I'm the guy over there in the corner, sitting in the cubicle. Hi. Who are you? I just imagine it's you guys. A lot of you guys really excited, glad to listen. At least that's the way I visualize you. So let's move on. So what are we going to do today? We're going to talk for the next 45 minutes or so about why does your product break. I don't mean you, your product, but I mean products in general. Why do engineered things fail? To do so, we'll look at three different elements today. We'll start our agenda by talking about mechanical failure modes. What are different ways that things can fail? And number two, we'll look at a specific failure mode, fatigue. What is fatigue? What do we mean by that? What causes it? What are some of the physics behind fatigue failure? And number three, we'll look at methods for assessing fatigue life. If we understand that fatigue is a failure mode, an important one we need to design against, then how can we use our engineering judgment? What methods can we use to either predict fatigue or to design against it? Because the last thing we want to have happen is what happened to this aircraft we see below. This is an airplane that saw one too many compression and decompression cycles while it was flying. The top came off and it turned into one of the first ever convertible commercial aircraft. So our goal today is to try to understand what would have caused this failure and also how we can design against it. So to do that, first let's look at structural failure modes or mechanical failure modes. How are all the different ways that things can fail? First off, we could talk about overload. The stress just gets above the strength. So stresses go above yield. Stresses go above tensile strength. And then the part will fail in either a ductile or brittle manner, depending on its material characteristics. Corrosion can also lead to failure. As a matter of fact, on the previous slide, that 757, I believe it was, from Aloha Airlines, was a combined fatigue and corrosion interaction. Creep can also be a problem. And what I mean by creep is elevated temperature causing mobility of molecules. So another way to put that would be at high temperatures, materials can begin to behave like taffy, can begin to move in a, to be technical, a viscoelastic or viscoplastic manner. In other words, time dependent, almost liquid-like. This happens in very high temperature applications with a number of metals. It can even happen at room temperature with, say, a particle board shelf that may be holding up a big old television at home. You may have a particle board shelf that you've noticed has slowly sagged. And that's because the glue that holds the particles of the particle board together is sufficiently weak, even at room temperature, to cause steady stress, to allow steady stress to cause time-dependent deformation. Other failure modes, wear, sliding friction, so force and velocity together can cause wear on surfaces. Impact as well, anything that can be potentially see an impact load. For example, the airframe we referred to earlier, we could have foreign object damage we have to guard against. Buckling. And lastly, we're going to focus today on fatigue. And you may wonder, why is it if we have 7 or 8 different failure modes here, why are we going to focus on fatigue? It's because reports show that a huge number of structural failures are attributed to fatigue. And the insidious or the haunting bit of fatigue is that it's something that happens without warning. And that is because fatigue damage, as we'll talk about today, is a cumulative problem. So we're used to thinking forensically as, hey, engineer, why did this part break? And we look and see, okay, what was the last thing we did with it? For example, a bridge falls down. What was the last thing that we did on this bridge? What could have caused this? And that can help us understand things like overload scenarios. But the fatigue scenario is not dependent on the last thing that happened any more than all the other things that happened beforehand. So fatigue is a cumulative failure mechanism, and because of that, it's much more difficult for us to design against deterministically, or to look at a loading scenario and understand, will that cause a failure or not? It's all the accumulated fatigue cycles over time that are going to cause a problem for us. So we need to address this. The good thing is we'll look at 3 methods for addressing fatigue analysis today. First, though, we need to make sure we understand what is fatigue. Here's some notable fatigue failures. In the upper left corner here, this is a steel bridge element from the Bay Bridge in Oakland, California. This is a crack that's big enough to put your hand into. This is an old bridge that you can see corrosion played some role in as well, probably. This saw cyclic loading due to a number of considerations, due to weather. So it gets hot on the top and cool on the bottom. That causes expansion and thermal stresses. Also, perhaps wind loading, traffic loading, and so on. In the upper right, this is a wind generation structure. This is taken just outside the office of my British colleagues in Rotherham, UK. This is you can see one of the blades has come off. There used to be an entire blade up here. So a fatigue crack started there because of wind loading, either from inertial loading from this thing speeding up and slowing down, or from wind gusting. Unfortunately, the entirety of this blade, once that crack progressed, flew through the car park, right to the parking lot of my colleagues, and had high risk of damage. In the lower left here, this is a fatigue example of a crack in a boat. These are the Liberty ships, they were called. If you want to do some lunchtime reading, take a look for Liberty ship failures. You'll find that the catastrophic failure rate of these was enormous, unfortunately, because of their construction and their lack of crack tolerance. And lastly, in the lower right here, this is a picture of your teeth, and you may say, why are we talking about teeth when none of us can actually design teeth? That's a good point, but a number of us design things that go into teeth called fillings, or design false teeth. All of these teeth have fatigue loading as we chew, and chewing over time can cause problems, and if any of you have ever had serious tooth cracking issues, you know that is a really painful thing, and your insurance ends up paying a lot for this. So to have fatigue-resistant dental implants is critically important for biomechanical or biomedical engineers to think about. So here's some examples of fatigue, but let's actually have a definition now. So pull out a non-technical dictionary, and it would say fatigue is a weakness in some material caused by repeated variations of stress. So repeated variations of stress causing weakness. Now, weakness is kind of a soft term for an engineer to go by. You know, we don't look at a product and say, we don't want it to have weakness. More specifically, the product specification or design guidelines might be, we don't have a crack visible. But weakness is kind of light. So instead, we can define this in a technical sense as initiation and growth of a crack or some flaw like a crack until it reaches a critical size. So this is a more engineering technical definition, even though an engineer didn't obviously write it because it's spelled right and it's even got punctuation that's correct. So obviously someone has helped along the way. The key from this is that we're saying that the part can fail after a while, even though the stress isn't that high. And that's the, as I said, the insidious part, or the surprising part, is that it's not necessarily that any one stress cycle is large. It's just that they happen a lot of times. And depending on our application, we can have stress cycles happen frequently, infrequently. We can have stress cycles come from any number of different events. And if the accumulated fatigue problem from them gets large enough, then we can be surprised by this fatigue failure. So we got to think about fatigue cycles, what causes stress cycles and such. So along those lines, what is a stress cycle? So fatigue and crack growth is driven by cyclic loading, and I've got a sine wave here of stress that goes from a minimum stress to a maximum stress, and we can just visualize in our head that this is a fatigue cycle here. If the stress didn't change, we wouldn't have a fatigue problem. So, you know, if we had the luxury of designing parts, the stress didn't change when they were being used, then we wouldn't have to worry about fatigue or durability. Now, the problem is that most parts that don't have changing stress, and parts that have constant stress, are just not being used. And the other problem is they're also not being purchased. So it's hard for us to continue to work on these products. So most things that we build see some usage characteristics that result result in varying stresses. So we have to think about the change of stress and strain. Stress or strain changes are what we call a fatigue cycle. From a design perspective, you may be used to thinking about what's the highest stress level, and that's great. That helps us understand the overload capacity. What's their factor of safety on strength, say relative to yield or relative to tensile failure. The maximum stress, though, doesn't help us by itself. In fatigue, we need to know the change of stress from maximum to minimum. We call that the delta S, or the stress range, or some people divide that by 2 and then they call it the stress amplitude. So everything we talk about today will be related to cycles and changes of stress. So let's think about total fatigue life. If we have things cycle long enough, we've already talked about how we can have failure result. So that means we have the ability to then start with a brand new manufactured or fabricated piece. So this is a relatively boring design, but it's a plate with a hole in it. Let's just assume that's what I've designed. At some point, that may come back to my desk in 2 pieces, and an engineer or designer may say, well, can you please explain to me why this happened? And you may have a good answer for that. You have to do some digging. Some of the digging is to think about things like part of the time in this component's life, from going from 1 piece to 2 pieces, some of that time was spent in starting a crack, starting a small crack, maybe even in a microscopic sense, starting a crack. And then some of that time was spent growing a crack in a macroscopic sense. And depending on what industry you're in, you may be very concerned about making sure that a visible crack doesn't start, or you may be more concerned with making sure a visible crack doesn't grow too fast. For example, if we were designing crankshafts to go into an engine, very hard to get at, a very highly stressed environment, I would not want to allow a crack to start, because to have a crack initiated is to introduce a lot of risk, large warranty claim. If, on the other hand, I was designing an airplane, airplanes are full of cracks, they just happen to be growing at a low rate in a predictable fashion. Another great example of things that are full of cracks would be, say, a sidewalk or a roadway. I'm not concerned in any way about a sidewalk that's got a 1 millimeter crack in it, or some kind of, say, porosity that results in a crack-like flaw. That doesn't bother me. What bothers me is if the crack gets so long that the roadway separates and that causes, say, a pothole or something that will keep people from using it in the manner that we intend them to. So we may think about crack initiation in our design philosophy. We may think about crack growth, or we may think about the totality of those two, which is, let's just make sure the part doesn't end up in 2 pieces on my desk. And with that in mind, then we can look at a couple different failure analysis modes or methods, fatigue analysis methods. Before I talk about 3 fatigue analysis methods, I want to look at this picture on the right side. What this is a tensile coupon. You've probably broken some of these at some point in your college career. These are usually cylindrical specimens that maybe are, say, an inch, a half inch, a quarter inch in diameter. And this one's been fatigued. Once it was broken, now we're looking down at the failure surface. And the interesting thing is, if we look through this failure surface, we can see that the surface just looks different. You could almost look at this as a map. The landscape has changed. Something looks different here than there. And this is a great way to illustrate what we mean by crack initiation and crack growth. We can see that the crack started here. For some reason, the stress was highest here, or there was some type of a defect, a material flaw in this region that caused stress to be magnified. We can see then that this crack grew going through this middle bit. If you look really carefully, you can actually see these concentric rings, like growth rings on a tree. Just like a tree grows every year, and if we cut down the tree and take a good look, we can see how old it is and what years were favorable towards tree growth that year. Likewise, we can see here, this is essentially charting out how the crack has grown. So any cycle that's big enough to push that crack a bit further will result in one of these new striations, or some people call these beach marks, like water or waves washing up on the shore of a beach. At some point, though, through this initiation and then growth phase, at some point the crack becomes so large, or the stress on that crack becomes high enough, that the remaining area can't cover that, can't carry the load anymore, and we have a fast fracture. So we have initiation, growth, and fast fracture all shown in this specimen. Now with that in mind, how do we attack these fatigue analysis problems? Well, it depends if we want to look at this in a crack initiation way. What do we have to do? How can we keep this crack from starting? How do we keep a visible crack from initiating? One method is to use what we call the stress life method. We'll have some more detail on this in just a minute. Some people call that stress life method the SN method. S for stress, N for number of cycles to failure. And that says if we can track stress cycles, we can track failure. We can also use another method called EN, or strain life. It gets the name EN because S was already taken for stress. So E epsilon, we're using that to denote the Greek value for commonly used for strain. This says that strain drives crack initiation, and this has an interesting twist on stress life in that it works for high cycle and low cycle behavior for reasons we'll get into in just a little bit. If we're worried about crack growth, if we're trying to figure out at what rate does this crack grow, or why does it break here, why didn't the crack continue to grow, we can use a crack growth methodology based on fracture mechanics. This uses a parameter called stress intensity factor, and we'll define this in a bit. And it says that in the existence of a flaw, or a crack, or say casting porosity, or a poor weld geometry, stress on that flaw will magnify our fatigue problem and allow that crack to grow, or give it crack driving energy. And we need to understand at what rate does the crack grow and when does it finally break. So with these three methods, we're going to look now in detail at SN, at EN, and crack growth, starting with stress life. So where does this stress life fatigue curve come from? There's a material set of properties, you could say, that will allow us to understand the relationship between the size of the stress cycle and the number of cycles to failure. Here's my tensile coupon again, and I play in a stress cycle repetitively over and over and over again until it breaks. Once it's broken, we call that constant amplitude loading. It's a repeatable cycle. Once it's broken, I can put on a piece of paper here. I can put one red dot for a broken specimen. And on the vertical axis, I've got the stress range. What's the size of the stress cycle? The maximum stress minus the minimum stress. And on the x-axis, this is how long did it last. So my one failed sample maybe is this red dot. Now, I can't make a relationship between stress and life by breaking one sample. I need to break some more, so I break 2. And then statistically speaking, I should probably do more than 2 to understand that relationship, so I may break 5 or 10. And in my case, I've got 16 dots here, so I've broken 16 samples. And I can see that I have this relationship between stress and life. The bigger the stress cycle, the shorter the life. That makes sense. Now, I can carry this plot around like this. This is my material fatigue curve for this type of steel, this type of plastic, whatever it was that I was using. I can carry this around. Or another way to do this is this guy Baskin in the early 1900s. He said we shouldn't carry around fatigue curves. Why don't we look at a relationship, a mathematical relationship between stress and life? And he proposed that most fatigue data like this generally looked like a linear relationship if we plotted the log of stress and the log of life. Now, in log-log space, a linear relationship is actually an exponential mathematical function. So we curve fit this, and now we have the size of the stress cycle and the number of cycles to failure is related by a power law. And that power is the slope of the fatigue curve, and this intercept is this value right here. So now we have two values, B and sigma f prime, the intercept and the slope, for this particular material curve. So now I've gotten the fatigue curve reduced from a graph into an actual mathematical relationship that I can use in a numeric way to solve for my fatigue problem. So how this is used, here's my SN curve again. How this is used is, first off, I can say, if I know how big the stress cycle is, let's see how long this will last. So if I know that my stress range is, say, 580 megapascals, I can look that up in my fatigue curve and say the fatigue life is about around about 100,000 cycles to failure. I can also turn my calculation around and say, maybe we have a design target. We need this thing to last for so long. So in an engine, how long should a valve spring last? Or on a railway application, how long should a railway axle last? Maybe in my case here, I've decided our product should last That's about maybe 600,000 cycles. So I can look here and say for 600,000 cycles, what's the allowed stress target? And I can say, let's design this part so the stress range is around 400 megapascals, and that will allow us to meet our known life target. So this is using the SN curve. There's a whole lot more detail to the SN curve than this, but today's presentation we're trying to look at it kind of an overview of a number of different methods. So I'm going to leave the detail alone for a different webinar. Now let's shift gears here a little bit and look at the strain life approach. The strain life approach is similar to the stress life approach, but this time we're going to test and break material coupons under known strain conditions. So you may wonder, why would we do this under strain conditions instead of under stress conditions? And that is because ultimately cracks start with microscopic deformation. So over on the right side here we have this diagram that shows that microscopically, if you think back to metallurgy a bit, most materials we work with have a crystalline structure. And that crystalline structure deforms under shear. So you can kind of imagine we have this deck of cards, this nicely organized deck of cards in our hands, and then we're going to shear that deck of cards. So imagine moving one hand towards you across the deck of cards, the other one away from you. And do that back and forth a couple times. And when you're done, the deck of cards will get kind of messed up. And you can kind of see this is how we visualize the deck of cards being messed up. Now this right here is the start of a crack in a microscopic way, in a way that engineers don't care to know about, to be honest. Engineers don't typically go looking for microscopic cracks. We look for macroscopic things. We don't calculate stresses in a microscopic way. We don't measure stresses in a microscopic way. We don't use FEA, finite element modeling, with microscopic elements. So this is conceptually what's going on, and you can see from this concept of this shifting deck of cards that it's deformation, it's strain that describes how messed up my deck of cards is. It's strain that describes that formation of that crack there. So really tracking strain, not stress, is the appropriate way to understand fatigue. So you may say stress and strain, wait a minute, I remember about these. I learned that they're equivalent. There's this elastic modulus, this simple scalar that separates the two, which is true under some conditions. But as we get past yield, we have a more complex relationship between stress and strain. So don't get confused into thinking that stress and strain are simply related, because under some loading conditions that may not be true. So what this means then in the end, we can run a series of tests and come up with what we call the strain life curve. And really, the strain life curve that I'm showing here looks very similar to the stress life curve. Effectively, this is the stress life curve, but now we've got this in strain instead of stress, and number of cycles or reversals down here. This is more or less the stress life curve divided by the elastic modulus. Now here's the unique thing. Notice that this curve, the strain life curve, has a band, or non-technically you may say this is a knee in the curve. This goes to show the difference between low cycle fatigue and high cycle fatigue. Stress life only works for high cycle fatigue because even though it was inherently tracking not strain, but the wrong thing, stress, it gets it right when stresses and strains are numerically, or have a scalar relationship, and that's in before yield, and that's high cycle fatigue. Fundamentally, the value of strain life is understanding low cycle fatigue. It gets high cycle fatigue right, and also it gets low cycle fatigue right. Stress life only gets high cycle fatigue right. So this is one of the benefits of using the strain life method over the stress life method, our ability to understand low cycle fatigue. Now let's move along here. Now think about, what if our design philosophy is tolerant of a crack? So what if, for example, we're designing a pressure vessel that can be cracked as long as the crack doesn't get big enough to leak our pressurized media out? Or designing an aircraft that can have cracks in it as long as we can take off and land a whole bunch more times before our airplane goes into its convertible mode, as we saw earlier. So we have to think now about, if we have a crack that starts microscopically, it can grow to become large enough to be what we'd call an initiated crack, or a macroscopic crack, a couple millimeters, so it's a macroscopic detail now. The stress at the crack tip can become very high. As a matter of fact, if you use elasticity theory, you can show that a crack will have infinite stress on the tip, which doesn't help a whole lot, because if that were the case, if you thought that would help, at some point you should go to your director of engineering and say, I was looking at this problem. You had this this crack in this part that I was looking at it, and I calculated the stress on the crack tip, and I think we got it all figured out. It's infinite. And then you'll probably get a weird look like, okay, so what do we do about that then? And you'll say, I don't know, but it is infinite, trust me. So elasticity theory falls apart here for us, and we have to approach this in a fracture mechanics methodology instead. So we introduce this thing called the stress intensity factor, which is not infinite for every crack. Stress intensity factor is related to a geometric factor, y. You can look this up in a handbook or use FEA to derive this. It's also related to the nominal stress, not the stress at the crack tip. Remember, that's not very useful because that goes to infinity supposedly. So this is the nominal stress, P over A or My over I, and also related to the length of the crack. So the longer the crack is under given stress, the more severe problem we have. The higher the stress is and the longer the crack gets, then we have an even more serious problem. So this is, you could say, a positive feedback mechanism. As the crack gets bigger, then it gets to be a more severe problem. And in the end, we can have failure if the stress intensity factor, which is based on the applied stress and the length of the crack, if that gets too high, then we'll have immediate failure. This is no different than looking at overload criteria that says we will yield if the material's yield strength is exceeded by the applied stress. Failure occurs if the stress is higher than the strength. Likewise, we can say that fast fracture will occur, or brittle, unstable fracture will occur, if the applied stress intensity factor exceeds a material property. And that material property is called K1C, or fracture toughness. And you can look this up in a handbook, and you'll find that it's extremely low for brittle materials like glass, and extremely high for ductile materials like unalloyed metals. So this will help us understand, will the crack fracture immediately or not? Now, if it doesn't fracture immediately, there's still the potential that it may at some point. So then we need to look at what rate is the crack growing. Remember, we had before the sample, the cross-section we looked at where the failure surface changed color and you could see the crack growing. So the previous slide helps us understand when will the crack finally have brittle fracture straight through. But in the meantime, at what rate is that crack growing? And we use this thing called a crack growth rate curve. And this is this says, let's look at how much does the crack grow per cycle in accordance to the size of the stress intensity factor cycle that's being applied currently. So this chart here shows what's the crack growth rate, how many millimeters does the crack grow per cycle. Hopefully we find that it's very, very small, at least small enough that we can take off and land again, and then have a mechanic repair the aircraft, as a function of how big the stress intensity factor cycle is. So at what rate is the crack growing per stress cycle applied to it? Over here on the right side, this is where fast fracture occurs. If the applied cycle becomes too large, then the crack growth rate becomes an immediate problem and we have fast fracture. This is the reason why something finally goes pink and breaks into two pieces. If that's not the case, though, then we can have potentially stable crack growth. And what we have here in the middle of this crack growth rate curve is a crack that's growing in a predictable sense up towards final failure. So there's a lot of product life that we can get out of some products as long as we're working with what we call tough or fracture tolerant materials or damage tolerant designs with redundant load paths. So this, you could say, is the fatigue curve for a macroscopic crack. So with those three methods in mind, let's think now about loading. We've talked a couple times today now about constant amplitude loading. I have this repetitive stress cycle here where it's not constant stress, that's not a fatigue problem, but rather this is a constantly sized cycle. We go to max to min, max to min, max to min over and over and over again. And we said before we can look at a fatigue curve and say, how long will this last? Or if we want it to last this long, then what's the allowed stress? Okay, that's easy enough. Now the challenge is, what happens if we have a fatigue loading scenario that's a little bit more difficult? For example, I'll call this one block cycle loading, where we have a moderate size cycle for a little while, and then a smaller cycle that happens for a little bit longer, and then a much larger cycle that happens longer after that. This top example might be if you think about, say, a railway application where we have a stress in an axle, and as the axle rotates, it goes through reverse bending. So this is it trundling along down the railroad track that's very smooth, and it's got one static weight it's carrying, which results in a rotating bending scenario. Now, this one down here, block loading, this would be, what if the train is partially loaded, and then unloaded, and then very heavily loaded, so the stress is changing in this kind of a simplified kind of block scenario. What will the fatigue life be then under this loading and that loading together? That's our challenge. Or even bigger challenge is what happens if we go measure load data? Or what if we introduce track roughness or wheel out of roundness or some kind of a random vibration of some sort or something highly more variable? Anytime you measure strain or loads data, we end up with these, what I would refer to as a squiggly line, or technically we'd call this a variable amplitude load history, with all these different, almost random looking cyclic content. So what cycles are in here, and how does this lead to potential for product failure? So we need to be able to address this fatigue loading that's not a constant cycle. And the way we do that is we use this thing called rain flow cycle counting, and we'll look at that in just a minute. But before we do that, I want to look at an analogy between fatigue damage and your bank account. A friend of mine that's non-technical once said, if you ever feel like you're losing an audience, you need to get out of a technical message and talk about money, because everyone knows about money. So here's my attempt at talking about money. So what's important in fatigue? How big are the cycles? And how many of them happened? So you hear me say this a whole bunch when we talk about fatigue. How many cycles of what size? How many cycles were there, and how big were those cycles? And how did they vary? Were they all the same size? Or were the cycles highly varied, as we saw in the last case on the last slide? The way this ties into your bank account is this. Imagine if you have a pile of money in the bank. So first off, congratulations, you're retired, let's say. You're accruing no interest on your bank account. It just sat there. As you spend, you're doing damage to your bank account. So if you want to figure out how long you can spend, the important factors here are going to be, we need to figure out how much do you spend each time. Every time you go extract money, how much is that? How much are you pulling out each time? And then also, how often do you do that? Do you go to the bank every day? Do you go to the ATM several times a day? So expenditure size and occurrences is like saying cycle size and cycle count. If we spend all of our money, then we're going to be broke. Likewise, if we have enough cycles of a large enough stress amplitude, we'll have completely damaged our part, and it too will be broke, like literally broke in two pieces. So we need to now understand, how do we count cycles? How do we figure out how big they are? And then what do we do? First off, how do we find those cycles? And secondly, what do we do with them? And how we find those cycles leads us into what we call rain flow cycle counting. We'll look at that right now. Rain flow cycle counting is like counting for fatigue. If you do vibration analysis, you're probably used to the fast Fourier transform. The fast Fourier transform is an awesome way to understand vibration. Rain flow cycle counting is an awesome way to understand fatigue cyclic loading. And the idea here is this is a technique that models stress-strain hysteresis loops. And if you really dig into this, you find there's an ASTM standard on this. You can read up if you want, or you can look in the nCode help docs if you have access to them to learn more about how this works. But the idea is that as stresses and strains are changing over time, they cause these things called fatigue cycles, or another way to call them is a hysteresis loop. Another name for this is an nCode logo. Yep, believe it or not, we actually got the nCode logo from a stress-strain hysteresis loop. So rain flow cycle counting is a strange mathematical or conceptual thing to get your head around, but the beauty of it is it's an awesome, efficient way for a computer to take a squiggly line of variable amplitude stress or strain history and count all the fatigue hysteresis loops in it, which means then it has all the cycles, which means that any of the techniques we've been talking about today, stress life, strain life, crack growth, any of those techniques can use this list of cycles to understand durability. Now that list of cycles is often plotted as I've shown in the bottom here. This is on the vertical axis, how many cycles of what size. And the size here I've chosen to show with two parameters, the strain range and the mean strain or the mean stress. So this diagram here completely encapsulates all of the counted cycles and how big they were. So this has answered the question for us. How many cycles of what size? The next question is, okay, great, I've counted for fatigue. Now, is it going to break soon? Or how long until it breaks? So how do we use this then? How do we use this with any of these fatigue methods? We use what we call Miner's rule. So Miner's rule says damage accumulates linearly over time. The more cycles there are, the more damage there is. Just like the more times you go to the bank and take money out, the more damage there is to your bank account. So this is, Miner's rule is the way of looking at a cumulative problem over time, or to be specific, not necessarily time, but over cycles. So Miner's rule says that each one of these cycles along the way, the moderate size, the small size, and the big ones, each one of them accumulates some amount of fatigue damage. It's like taking up life budget. It's taking away a little bit of life. And what's the life? Well, we can calculate that. We could say, look at the moderately sized cycles that we've called big S1. And we can say, on the SN curve, if we have that happen, it's allowed to happen big N1 number of times. Well, how many times did it happen? Small n. So the ratio of small n to big N, the ratio of the number of times it did happen to the number of times it can happen, is like a little fraction of life that's been used up. It's like we've taken a little bit of our budget away by going to the ATM that day. That little fraction is called partial damage. And we can continue to do that and look at these partial damage fractions for each of these different cyclic loading scenarios. And then we can say the total problem, the total fatigue damage caused by all of these cycles is the problem caused by this, plus the problem caused by this, plus the problem caused by this. And that is Miner's rule. The sum of all the damages from each cycle on its own adds up. And if the damage exceeds 1, that means we've completely broken the part. That means we have a crack. We have a big, serious problem. This is like saying if the sum of my big expenditures and small expenditures and moderate expenditures all exceeds my total trust fund in my bank, I have a financial problem. If the fatigue damage is less than 1, if I haven't spent all my money in 1 month, then I can project ahead how many months can I spend money. So if I were to calculate the total damage from this stress history is, say, 0.15, that means I'm 15% of the life consumed now, which means that 1 divided by 0.15, I can repeat that. That's about, I think that's about 7.5 times. Reciprocal 0.15 is about 7. So that means I can repeat this entire stress history 7 times before failure. That's Miner's cumulative linear damage summation. Some people call this the Palmgren-Miner rule. For some reason, the Miner rule has stuck for most. So that's how we use this record of cycles, of how many cycles, of what size, to our advantage. So with that background, now let's look and see how would we go about actually doing a fatigue calculation. We have a couple different routes. First route over here on the left side is we can use a measured stress or strain history. In this case, this is a strain gauge. I've put a strain gauge on the part myself. We'll take a look at the pros and cons of this method in just a minute. We could also have a similar kind of concept, but do this virtually using finite element analysis instead. So we'll look at these two and compare and contrast and see how what value each one brings to the puzzle for us. First off, using measured strain gauge data, the idea here is that we're going to put these strain gauges in hotspots. So we're going to measure the structural response with strain gauges. And then we'll end up with a squiggly line or a variable amplitude strain history like this for every hotspot strain gauge location. And we could use that data in a couple ways. We could use it to look at, if we're worried about overloads, we could just look and see how high is that peak stress relative to a fatigue strength or a material strength characteristic, say like yield strength or like tensile strength. That would help us understand the overload failure criteria. Now, in a fatigue sense, though, we'd want to go through all the stuff we just talked about, which is counting cycles and so on, and do that fatigue stuff for those critical locations. The advantage to doing this is that this has been done for quite some time. Strain gauges have been used, believe it or not, since just after World War II, so over 60 years now. So it's historically accepted as you measure strain gauge data and good for you. One of the other advantages to using measured strain gauges is that they record strain under all sorts of conditions, whether the loading is typical or atypical, or whether there's some nonlinear strain geometric effects going on, whether there's a thermal effect that's involved. Whatever the deformation of the structure is will be recorded by that strain gauge, and that can be a good thing because we can sometimes oversimplify loading scenarios in our head and then collect measured data and then find actual loading is maybe not quite so simple, and we can learn then about characteristics of customer usage and so on. The downside to this is that we need a strain gauge in each hotspot, so this can be a bit laborious at times if we're working with, say, a large structure that needs 100 or more strain gauges to understand all the different hotspots. The other downside is that the strain data is limited in use if the design changes. So, for example, if this tube structure here, if this is a strain gauge that maybe is near a weld, that's good information until someone says, you know, let's actually up the gauge of the tube, and then we'll go to a 2-pass weld instead, and then also maybe add a gusset. And then suddenly we say, oh, that's strain gauge data. Oh, yeah. Well, the design changed, so that means the strain gauge data is not very useful to us anymore unless we can come up with some kind of a relationship between what the strain was before and what it is now. So sometimes the strain gauge data doesn't stick around as useful data for very long. The last downside to this approach is that we need to have a working prototype to measure strains on, and this is the kind of thing that in modern engineering practice, everyone, say every director of engineering or chief engineer or say like a chief product development officer says, why do we have to build things just to show that they break? Why do we have to build prototypes just to test them? We prefer not to do this. Now that leads us in to our second fatigue method, and that is using finite element analysis, using structural analysis. So the idea here is we use finite element modeling to predict virtual stresses and strains, and then we'll think about those loads changing over time to cause virtual stress cycles, and then we'll use the concepts we had earlier. So if we have virtual stress cycles, then we can predict virtual fatigue life. And in the end, then we end up with a plot like this in the upper right that is the geometry with a fatigue life contour plot. This is not stress in the typical FVM sense. Now this is actually fatigue post-process to get into life. How many cycles, how many hours, how many landings until failure. So the advantage of doing this is that we don't have to build something just to test it. This is what chances are your senior management in your company wants you to do. Get away from physical prototypes. Certainly the board of directors and investors in the company want everybody to do this because of cost and timing reasons. It's very easy then to assess design changes. We can look very quickly at, well, what if we change this radius right here? Or if we add a stiffening gusset of some sort? How will that impact our fatigue life? We don't need to go back and rebuild a prototype, recollect strain gauge data. We can do this kind of FEA pretty quickly. And then lastly, a wide variety of FE solutions are supported these days. Any way you can figure out how loading becomes stress or strain will be useful then for a fatigue calculation, whether that's a static solution or linear or nonlinear or transient or dynamic or involving contact or involving impact or plasticity or whatnot. All of these finite element solutions, if they're capable of producing good stresses, means that our fatigue calculation has a chance of working, being useful to us. A disadvantage here is that we need good hotspot stresses just to turn that last advantage around. That is to say, if your FE solution doesn't get the right stress, then the fatigue calculation is going to be off base as well. We don't, unfortunately, have two negatives making a positive here. We have to have good stresses. Just like we said when we measure strain gauge data, we have to have strain gauges in the hotspots or some way of understanding hotspot stress to be able to do fatigue calculations. And then lastly, the real work can be very nonlinear in some ways. So sometimes the modeling we do is a simplification of the actual, say, geometric loading or the maybe impact or other things like that. And I think that this disadvantage is going away over time as we have more robust finite element solutions out there. But we still have to think about what is the difference between what we're modeling and what's actually happening out there in the real world, and then try to rationalize that difference or understand it in our finite element-based fatigue calculation. So all of these concepts can be put into play using nCode software. nCode has been around doing fatigue software like this for looking at stress life, strain life, crack growth, and a whole host of digital signal processing and such for over 30 years now. This is our bread and butter. We've got a couple different products here that I'm going to highlight just in the next minute or so on the screen. On the left side, this is Design Life, and this is doing the finite element-based fatigue calculation I talked about on the last slide. So this is using results from Abacus, ANSYS, Nastran, Radios, and so on. If you have measured test data, then Glyphworks is probably the tool of choice. This is working with measured time series data and doing all the fatigue stuff we talked about today. And additionally, being able to do vibration analysis, performance analysis, understanding general signal processing kind of calculations. And our last product here is automation, which is maximizing the ROI of the measured data by automating processes and looking at trending reports and such. I'm not going to go into any detail on how these all work because we've had other webinars like that. If you want to see those webinars, I suggest you take a look at ncode.com. We have a whole host of recorded webinars from previous sessions, and if you go there, you'll be able to learn more specifically about each of these software components inside the nCode software suite. So with that, now I'm going to